part of the study, which is practical transformer. So previously you learned about the ideal transformer, which is very easy. Okay, so you just have the voltage input and then output. Okay, now it is much more difficult because this is a practical transformer. So in the practical transformer, you have a winding resistance, flux leakage, finite permeability, and core losses. Okay, so because of these 4 things, you have to include inside the model. So what is you have to include? So if you see here, so let me draw this. Okay. So this is sec2, E1, E2, E1. So this one is V1 and this one is V2. Okay, so in ideal transformer, V1 is equal to E1, E2 is equal to V2. But for practical transformer, that's all changes. Okay, so for winding resistance, you can see here. Okay, you can see here there is a winding. Okay, you remember, if you recall, in wire there is actually resistance, very small resistance. But if you do the winding almost 100, 200, 300, this resistance can be severe. So how to represent this winding? Okay, this winding resistance. So you just add resistance in series. Also at the secondary, because you have the secondary winding. Okay, so that is the practical one. And then you have the leakage flux. Okay, flux leakage. Recall back. If you can see here. Okay, if you can see, there is a leakage flux. If you recall in the magnetic circuit, when you do a winding, the flux is not fully inside the core. It will leak, okay, at the outside. So how to represent this? So basically just add winding, okay, inductor here. Okay, you have inductor here to represent the flux leakage. Okay, and then you have core losses. Okay, when you have core losses, you have to add another circuit. Okay, you have core losses in the form of resistance. So what is core losses? Okay, recall back the theory in the magnetic circuit. Okay. I'm not sure whether, okay, the theory of the transformer. Okay, you remember you have hysteresis, loss, and eddy current loss. Okay, this loss, you can represent it here. So this one is R1, this one is X1, this one is R2, this one is X2, this one is RC, okay, core resistance or core losses. And then you have a finite permeability, okay. When you have the winding here in the primary winding, okay, actually you need to have a certain amount of flux, okay, to start the system. So this one can become a losses, okay, something like this. So XM. So this one is a magnetizing reluctance. So basically, when you want to start a transformer, basically you need to have a certain amount of magnetizing current, okay, to start the transformer before you can start everything. So this one represent as this one as a inductor in parallel. So basically this is the practical model. Okay, make sure you know how to draw this. Okay, in practice, magnetic core have finite permeability, a magnetized current. Okay, so you have a magnetized current. This is IM. Okay, is required to establish a flux in the core. So this is what I'm saying. You need to have a current, okay, minimum current. Okay, and then the core losses. So this one is IC. So this one is caused by the hysteresis loss and the eddy current loss. Make sure you recall back the theory. Okay, so you can see here the core losses and the magnetizing component. Okay, so if you so this is I1. Okay, so this one is I0 and this one is I1 bar. So basically it's not fully, I1 is not fully goes into the transformer. Okay, so you can see here the relationship changes. Instead of N1 divided by N2 equal to E1 divided by E2, and I2 divided by, instead of I1, it will become I1 bar. Okay, it's not because some of the current goes into the I0. Okay, so I1 is equals to I1 bar plus I. Okay, make sure you know the relationship. So this one is N1, N2. Okay, so there's a diagram. So this one, maybe later I will show you the phasor diagram. Okay, so this is the winding resistance and leakage plug. I already explained it to you. So winding resistance you present as R1 and R2. Plug leakage, okay, you present it as reactance, okay, reactance, I think, reactance, okay, X1 and X2. Okay, so this is the full model of the practical transformer. So this is I0, okay, IC, IM. Okay, make sure you know the current, the voltage, the resistance, then the X. Okay, and make sure you know what is all represent. The reactant, the resistance, the magnetizing component, and the core losses. Okay, so this is the phasor diagram. Okay, so how to draw the phasor diagram? So this one is also a mostly theory. You can see here. You set the V2 as a reference. Okay. Okay, and assume that you have a ZL is a lagging. Okay, lagging power factor. So you have I2. Okay, you have I2 here, and because of the R2. Okay, remember I2 and R2 is in phase. This one is I2 R2. Okay, and X2 is 90 degree with the current. Okay, 90 degree with the current. So this is I2 X2. Okay, which is the voltage at the reactance. Okay, and the voltage at the resistance. Okay, and if you transfer this, okay, this current here, okay, and this current here, okay, you do a loop here, the Kirchhoff voltage law. Okay, you will get the, so you get red, blue. Okay. You get E2. Okay, so basically E2 will changes. Okay, so if you make V2 as a reference, E2 will not be 0. The angle is not 0 and the voltage is also not 0. Not the same as the V2. So E2 not equals to V2. Okay. Make sure you know the relationship for the practical transformer. Now for the second one, you can see here. Okay, for this one, you make E1 as a reference. E1, okay. And the same thing, assume that is this one is what you call lagging power factor I1. Okay, so of course you have a parallel current here. Okay, parallel. Okay, I1 R1. Okay, remember resistance always parallel to the current. Okay, so this one I1 X1. So this one is 90 degree, remember? Okay, because this is a reactance. Okay, and then you get V1. Okay, so for I1 and I0, okay, remember I1 is equals to I1 bar plus I0. Okay, so I0 is what? So I0 is equals to Im plus I core. So something like this. You have Im. So Im is 90 degree. Okay, inductor. Remember, inductor, it is 90 degree. I core is similar to E1 because it is in parallel. So this is I core. Okay, this is Im. Okay, so this is E1 because it is in parallel, and IC is resistant. Is parallel because it is resistant. This is inductance. So you have to do this, something like this. You have I not. Okay. So you have I not something like here or something. For this case, maybe I have to redraw this. Okay, I not. So you get the E1. Okay, so this one I not I1. Okay, so basically you have to this one transfer to here. Okay, this one is I not, this one is I1. Okay, it's a little bit confusing, but try to understand this. Okay, this is the phasor diagram. Okay, this is usually come out in the theory. Okay, so make sure you understand this, how to draw the phasor diagram. And then you have the approximate equivalent circuit. Okay, so you already have practical circuit here. Okay, which is look something like this. Okay, okay, which is look something like this. But this one is very hard to calculate, to analyze, okay, because there is a series circuit in the middle. Okay, so how to solve this? So you have a this is the practical circuit, and then you want to simplify. Okay, it become a approximate. Approximate model. Okay, so what is done is basically you just move in the primaries in the here. Okay, you just move it. Okay, you can see here the RC and LM is at the middle. Now it is moved at the left side. Okay, that's it. This is the approximate equivalent circuit. Okay, so since no load current is very small, so I naught, okay, I naught is basically the no load current is very small. Okay, only 3 to 5% of the full load. Okay, the RC and XM can be moved closely to the supply without a significant calculation error. Okay, so the calculation become easier. So if you want to make the calculation more easy, you just move the RC and XM at the left side. That's it. Because they're still different, but the difference is not too large. Okay. So this is the calculation. Okay, you can see here, you can move it into the secondary side. Okay, sorry, the primary side. Okay, if you combine this, okay, if you combine this, it will become something like this. So easier for you to combine. Okay, so let me show you how to do this one by one. Okay, so you have an approximate circuit. Okay, this is not the practical. Practical is the RC and XM at the middle. So this is the approximate circuit. Here you have inductor here, and then you have this one inductor and this one inductor, and then Z2 or Z load. Okay, so you have R, C, XM. This one is V1. Okay, this is I1. This is I0. This one is I1 bar. Okay, this one is R1. This one is X1. Okay, this one recall back A squared R2. Okay, if you bring the secondary side to the primary side, make sure you know how to change it. So this one is E1 or AE2. Okay, AE2. This one is A squared X2. Okay, Z2 is, okay, this one is no longer Z2, it's Z2 bar, where, okay, Z2 bar equals to A squared Z2. Okay, Z2 bar means that you bring it to the side, other side. Okay, so Z2 bar is just a Z2 bring to primary side. Okay, what it means that Z2 bar. Okay, so this one will become AV2. Okay, AV2 or equals to V2 bar. So this one is I2 bar equals to I2 divided by A. Okay, so make sure you know all the relationship here. Okay, can anybody understand so far for this? Is it okay?
I will need more
Okay.
practice.
Okay. So maybe today you still don't understand, maybe later you can understand it, because this is a lot of component here. So this is just what I'm trying to tell you, just to transfer everything at the secondary side to the primary side. Okay, you can also transfer the primary side to the secondary side, but it is much more complex. Okay, try to avoid it, but usually we transfer the secondary side to the primary side. So this is the plot that the phasor diagram. So you can see here E2 is the reference. You can see this is the drawing, same as before. Okay, try to understand this. Okay, the same concept. Okay, and for this case, okay, remember this is V1 is parallel to this circuit, means that the IC is now follow the V1. Okay, okay, this one already explained it. Okay, I think for example 3, okay, I give you example 3. Okay, so okay, a 100 kVA transformer has 400 turns. So try to extract the information first. Okay, so S is equals to 100 kVA. Okay, So primary turn N1 is equals to 400 and the secondary turn is 80. So this is a step down transformer because the number of winding at the second side is much more lower. So you can see here the primary and secondary resistance is R1 is 0.3, R2 is 0.01. And the leakage reactance is X1, okay, leakage reactance. That's why you have to know what is leakage reactance, okay, the resistance and everything. So 1.1 ohm, okay, all of this is ohm, okay, and X2 is 0.035 ohm, okay. The VS or V1, the voltage supply is 2200 volt, okay. So calculate the equivalent impedance referred to the primary side. So impedance means that the Z. So ZEQ is basically just R1 plus J X1, okay? R1 plus J X1 and don't forget a J, you have to put the J. And of course, you have to move all the secondary reactance and resistance or secondary impedance. Okay. So this one is called Z2. So this one is Z1. Okay. So what it means that, let me, so ZEQ is just Z1 plus alpha squared Z2. Okay. So Z1 is 0.3 plus J 1.1. Okay. So Z1 is equals to R1 plus J X1. Z2 is equals to R2 plus J X2. Okay. So plus alpha, okay, you have to calculate alpha first, outweigh, get the ratio, sorry. So the turn ratio is N1 divided by N2. So 400 divided by 80, you get 5. So 5 squared 0.01 plus 0.035 G. So what is the answer? Can you calculate the answer? You have to use complex calculator, complex mode. Okay. So you get 2.05. The angle is 74.44 degree. So you get this one, answer ohms. Okay, this question asks you to refer to the secondary side. So to refer this to the secondary side, you just, okay. So ZEQ bar is equals to okay, recall back, forget already. So Z1 is equals to alpha squared Z2. So this is Z1. So Z2 is basically, okay. So ZEQ divided by alpha squared. Okay. So ZEQ is 2.05 angle 74.44 divided by pi squared. Okay, so you get 0.082 angle 74.49 ohm. Okay, so that is how you calculate the approximate circuit. Okay, there should be more example, but I still don't have any example yet. So maybe later I will give it to you next week. Okay, and for next week, we also continue with the transformer test. Okay. So for next week, okay, on Monday, I will discuss with you, okay, about the test. Okay, I give you practice, okay, a little bit of practice before the test at the night, 9 p.m. And we continue with more example and the transformer test at the Tuesday. Okay, that's all for today. Today's class. Is there any more question you want to ask?
No, doctor. Thank you very much.
Okay, if there is no more question, I will end the class. So thank you.
Have a nice day, doctor.
Thank you,
Okay,
doctor.
have a nice day.
Doctor.
Okay, welcome.